Okay. Let me also remind you that we slightly changed the schedule for next week. On one of the older schedules, Tuesday appears as a lab date, but it's actually Thursday. So Tuesday will be a regular lecture here, and Thursday will be the lab. And for the lab, we meet in 1115. That's on the handout for the first day. Also, if you're not registered for class, you don't have automatic access to Stellar, to the website. So we can manually add you, but you'll have to let us know. Just send email to Professor Marzari and myself, and even better is if you send email to both of us. And then we'll manually add that. And we'll put links there, things like articles, things that may have restricted access, copies of the lecture notes, things like that will appear there. Okay, so what I want to go do is go back to pair potential models, and what we're going to do today is talk a little more in detail about the sort of formal or conceptual failures of pair potential models, and then how they get addressed with other empirical models. But before I do that, I wanted to see if I can get this into place. Guess not. Go through a few practical issues, since the first lab is actually on using pair potentials to model things, so you get a bit of an idea. So in a pair potential model, your energy is written pairwise, and so essentially what you need to do between every pair of atoms, every couple ij, essentially need to evaluate the distance between them and then put that in some kind of energy function. So this is clearly an n-squared operation where n is the number of atoms, since you have to look for the distance between every atom and every other atom. So if systems get extremely big, and that's often the reason why you want to use pair potentials rather than, say, a quantum mechanical method, n-squared will get very large. And people do kind of tricks. If you have millions and millions of atoms in your simulation, if you know ahead of time that some of them are very far from the atom on which, say, you want to calculate energies or forces, then you really never want to look for their distance. So people do things like keeping neighbor lists. So literally, for every atom, you would know, well, these other atoms are possibly in its neighbor environment. Okay? So then you really only have to look for distances with those atoms. So if you have a solid, that's great, because if you have a solid, then the topological relation between atoms will not change much during a simulation. Of course, if you're simulating a gas or a liquid, they will. And then what you have to do is essentially update the neighbor lists regularly. Okay? And so there's overhead associated with that, but the benefit you get is that you essentially have an order n system, okay, rather than an n-squared system. I'll show you in a second some large-scale simulations. Very often, you will want to relax a system, so get it to its lowest energy, and very often that's done by calculating the forces on atoms and literally stepping down the force. If you want to do dynamics, Professor Marzari will later teach you molecular dynamics. You also need the force, because the force will tell you how much atoms accelerate or decelerate. You will need to calculate the force, which is a potential derivative, so you're essentially calculating the derivative of the total energy with respect to a given position. Okay. Same deal. That's an n-squared operation. Okay. You have to sum over pairs of atoms. Well, you have to sum over all atoms for the force on a given atom, but since there are n atoms, it's an n-squared operation. In a lot of codes, the minimization is done by very standard schemes, things like conjugate gradient, Newton-Raphson, sometimes often trivial line minimizations, where you literally just calculate the force and assume some kind of elasticity along the force path. And so if you know the force, you assume you know what the curvature is of the energy in that direction, you kind of can make an approximation to its minimum, and you do that iteratively. So you can do that with very large simulations, and I wanted to show you sort of one of the leading edge ones. I got to get out of PowerPoint for that. If I can make that work. Okay, here we go. So what I'm going to show you is a order million atom simulation. This is essentially a cube of 1,000 by 1,000 by 1,000 atoms. No, that would make more than a million. Forgot to write down what it was. Yeah, I wrote down 1,000 by 1,000 by 1,000 atoms, so that'd be a billion atoms. And essentially, what's being done, what you see is a notch on top and above. Because there's so many atoms, you don't see the discrete resolution anymore of the atoms, so this thing starts to look like a continuum. And it's being pulled from the side, so you'll see the crack grow and dislocation sprout. This is a simulation from Farid Abraham when he was at IBM. And of course, if you have big computers, you can do big simulations. So let me sort of show it to you. So what they actually did was they showed just the dislocations by counting under-coordinated or over-coordinated atoms. So what you're actually seeing is the dislocation lines. I mean, if we plotted all the atoms, you wouldn't see anything. Huh? You just kind of see green everywhere. And that's sort of zoom up. So this is a molecular dynamics simulation, and you'll learn later more about that, where you essentially just do Newtonian mechanics on atoms. And so this is one of these very large-scale things that you can actually do with potentials. Now you could ask yourself, what did I learn from this? You know, this is the kind of work that, my personal opinion, is scientifically not necessarily all that relevant, but it's pioneering work. You know, this is like Lewis and Clark who went to the West. You could always say, what did we learn from them? You know, maybe not a lot, except that you could get the Pacific. But it's kind of pioneering work. You know, when people do these kind of simulations, it's not as much for the science as it's probably for pushing the envelope and seeing, you know, what can you do with enormous computational resources. You really have to fine-tune your algorithms, you know, your parallelization schemes. So it's kind of like, you know, flying to the moon, which may have not brought us much, but there was a lot of technology fine-tuned for that. So that's one of the reasons I wanted to show it. Okay, let's go back here. Another very practical issue that I'm sure a lot of you are familiar with, since you, even, you know, when you have a billion atoms, it's actually still very small. I actually think if you do the calculation, a million atoms is, for a lot of materials, a cube of just about 200 angstrom on the side. So you're still, if these were finite systems, would be very small systems. So to get rid of boundary effects, you almost always use what's called periodic boundary conditions in simulations in as many directions as you can. And of course, what the periodic boundary conditions mean is that if you have some unit, you essentially repeat it next to it. So this end here is the same as that end. And this end here is the same as that end. So people always ask you, how many atoms do you have in your simulation? And the answer is infinite. Okay? It's just that you only have a finite number of degrees of freedom. Because it's, you know, these atoms here do exactly the same as these here. Okay? But the answer is infinite. So we don't really work with small systems, or rarely. I mean, sometimes we work with finite systems. But, so what's the repeat unit you use? Well, if you're studying a periodic material, then it's easy. You know, if you study, say, a perfect crystalline material, here's a perovskite unit cell, that's what you repeat. Because the material already has periodicity implied in it. So at that point, you're actually not making any approximation. You know, you're not enforcing anything on the material, not when you do a static calculation, that it already doesn't have. Now, of course, when you do dynamics, you're enforcing something because you're saying that, you know, in dynamics, the translational symmetry is temporarily broken because this atom can vibrate independent of that one. Okay? And so then when you impose periodicity, you are imposing that these vibrate together. So in some sense, you're imposing a cutoff on the frequencies of vibrations that can occur. If systems don't have periodicity, you typically tend to enforce it. You know, if I took this perovskite and I made one defect, I took, say I wanted to study oxygen vacancy. So I take out the oxygen vacancy, I lose all translational periodicity now. Okay? But what you do is you tend to impose it back by repeating the defect. It's going to be slow. So, you know, let's say I've taken out an oxygen here. I repeat the defect so that in essence, I just have a bigger unit cell, but it's one with a defect in. This is now my unit cell. Okay? And that's called a supercell approximation. Okay? So you make a cell that's big enough so that you hope that these defects, don't interact. Because then if you have, you know, n cells, your calculation just has the energy of n defects. Okay? And the critical assumption is, of course, that they don't interact. Because if they interact, then you're not modeling an isolated defect. You're modeling, you know, a defect that's interacting with other ones. So how do they interact typically? This is kind of important to know, you know. This is one of these things that you're going to do in the lab. You should always check convergence if you can. The problem is that often you already work at your computational limits for size of supercells, so it's easier said than done. You know, in an ideal world, you say, well, I calculate bigger and bigger, and if the answer doesn't change, you know, I take it. But usually you work so much at your computational edge already that you can't make it bigger and bigger. A lot of people forget that, you know, to check convergence, you also can make it smaller. Huh? You know, and if it doesn't change much, you were probably already converged. But it's useful to know how these things usually interact with each other. So that gives you some sense of how far you have to go. There's often the direct sort of interaction. If you work with a pair potential, then you can actually see what the range is of the pair potential. Okay, that's usually not the problem. Rarely do you have potentials that are relevant large enough over large distances that you need to make really large supercells. But there can be other energetic effects. You know, if you have electrostatics in your system, that will give you very long range interaction. If that's a charge defect, which it is in a perovskite, you will have a very strong. Actually, if we truly did a charge defect in that supercell, what would happen? If that supercell became charged, so let's say I took out an oxygen 2-, which means the supercell now has a net positive charge. What would happen? You'd have an infinite energy, okay? Because you would essentially have charges, okay, a positive charge interacting with only other net positive charges, okay? And at any distance, if you do an infinite system, that gives you an infinite energy, okay? So that's something that you would have to explicitly take out. Now you say, well, you know, I'll compensate with a negative charge, okay? Because that's what happens in reality. If I take out an oxygen, those 2 electrons of that O2- are going to go somewhere, so it's going to create net positive charge. But so then you have a dipole, okay? So let's say I have sort of plus, minus, and I have a dipole now. So now I have dipoles interacting. Dipoles will not give you infinite energy, but they will give you a fairly long-range energy tail. Okay? And if you're smart about it, so the brute force way to convert supercell calculation is always to push them as hard as you can and, you know, hope and sort of see the energy converge of the defect. But if you're smart about it, you can often do much smaller cell calculations and explicitly take out the term that's the defect-defect interaction. Okay? Which is, if you know that this is a dipole, you know what the form is of it, and you can take it out. Okay? Other things that often cause havoc is relaxation. If I were to put a really big ion in the center of that perovskite unit cell, okay, I would build up a strain field, and the different defects would interact through their strain field. Okay? So rarely do you actually interact through the direct energetics. You often interact through secondary effects. Okay? Another way they often interact, which is very indirect, if you put in your defect and you relax the supercell, the volume of the supercell, okay, then that will interfere with the relaxation of the supercell next to it. Okay. So you get a strain field just through the homogeneous, you get an extra energy term just through the homogeneous strain interaction. So these are all things to consider when you do supercell calculations. we're trying something new where we save the annotations we make on the slides, but it seems to be really slow. So I may not be able to keep that up. Okay, so this I went over, the kind of convergence. You know, here's a typical example. I don't know if this is typical. This is the vacancy formation energy in aluminum. Now, this is done with quantum mechanics versus the number of atoms in the supercell. And, you know, this is one of these that you really don't know if you're converged. I mean, it depends on how accurate you want it. If you really only care that it's between, you know, 0.7 and 0.75, you're probably okay. But if you did this point and that point, you'd probably think you're converged. But then if you look at the next one, you're actually going back up a little bit again. So it's sometimes very hard to figure out whether you're actually converged. Okay. So that was a few practical issues to sort of start gearing you up for the lab. What I want to do now is talk explicitly about some of the formal failures of pair potentials and go on to correct them. And the first one is the vacancy formation energy, which is, if you look at historically, you know, when people started doing simulations late 1950s, 1960s, into the 70s, people thought that, you know, whenever there was something wrong with the outcome, they just needed better parameters in the potential. And it's actually rather recent, sort of 1980s, that people figured out that there were really formal problems, that there were certain things you could not get right, never, with a potential because of the problem of the form rather than of the parameters. And a critical number in that work was actually the vacancy formation energy, which nobody could ever get right. And I'll show in a second why. Here's an FCC crystal, and so let's calculate the sort of pair approximation to the vacancy formation energy. Okay, what do I do when I make a vacancy? What I do is that I take this central atom and I move it somewhere else in the bulk. Okay, so in some sense I make my system one side bigger. So let's calculate the energy balance of that. So the vacancy formation energy. Okay, what do I destroy? I destroy 12 bonds, because this atom is coordinated 12-fold in FCC. So I destroy 12 bonds. So I lose 12 times the bond energy. But then, of course, I put it back somewhere in the bulk. And so I gain the cohesive energy of one atom. Okay, and what's the cohesive energy per atom in FCC? It's 6 times the bond energy, because there are 12 bonds around an atom, but every bond is shared between 2. Okay, so there's 6 per atom. So the vacancy formation energy is really minus 12 times the bond energy plus 6 times the bond energy. So what it is minus 6 times the bond energy. So essentially, it's minus the cohesive energy. The cohesive energy per atom. And that's essentially what you will always find with pair potentials. Now, I did a static approximation. I assumed that all these bonds were kind of unchanged as I took the atom out. In reality, if I take that central atom out, the atoms around it will relax somewhat and change their bond energy. But you'll see this when you do this in the lab. That'll make it from like 1 times the cohesive energy to something like 0.9 or 0.95 times the cohesive energy. Essentially, you find in pair potentials that the vacancy formation energy is about the cohesive energy. If you look, on the other hand, at experimental results for the cohesive energy, here's some experimental data. So this is for FCC metals, and this is for Lennard-Jones and for noble gases, the ratio of the vacancy formation energy to the cohesive energy. And what you see is that in the noble gases, which you think of as well described by pair potentials, you're reasonably close. Okay? Because remember, noble gases are just inert shells interacting through van der Waals interaction, and that's how we came up with the Lennard-Jones potential. But if you look at the metals, the vacancy formation energy is actually only a small fraction of the cohesive energy. Okay? And we can never get that low with pair potentials. Never. Okay? Unless you maybe really, had the most odd form of a pair potential. But the reason is because there's certain physics missing from pair potentials. Okay. So, actually, let me go back for a second to the pair potentials. What's the physics here of why the vacancy formation energy is so low in real materials? Remember what I said before, that bonding in metals, the bonding energy goes not linear in the coordination number. It's more something like a rough approximation would be the square root of the coordination number. But essentially, when you go from 1 to 2 bonds, your energy goes down a lot more than when you go from 11 to 12 bonds. Okay? So why is the vacancy formation energy so low? Well, if you think about it, what do you do when you take out an atom? You make a lot of the atoms around it go from 12 coordination to 11. Okay? So they lose a lot less than, 1/12 of the cohesive energy. Okay? Because the cohesive energy you could think of is the average of all bonds. Okay? But around the vacancy, you're just reducing the coordination from 12 to 11. You could actually make a simple model. If you said that the cohesive energy was some constant times the square root of the coordination. Okay. So rather than linear in the coordination, which is what we would get in pair potentials, if you calculate the vacancy formation energy in this model, let's do it for FCC. In FCC, Z is 12. The vacancy formation energy, what would it be? Well, if we put the atom somewhere back in, we would gain Z times the square root of 12. And then as we take it out, what do we lose? For 12 atoms, okay, we go from coordination 12 to 11. Okay? So this is the atom in the bulk. This is actually the change around where we made the hole. And if you actually calculate that, the vacancy formation energy over the cohesive energy, you find that that's 1 plus 12 times the square root of 11 over the square root of 12 minus 1. And it's about 0.49. So in a square root model, you're already much closer to the experiment where the vacancy formation energy is a much smaller fraction of the cohesive energy. Okay. Another critical piece of information was surface relaxation, which people had been seeing with leads. If you look at a metal, typically if you create a surface, the difference between the first and the second layer becomes smaller. So in a metal, the first layer tends to relax inward. Okay? And can somebody explain me why that happens? And typically you don't see this. In pair potentials, you very often have about the same distance. So the first to second neighbor distance is often bulk-like, and in some cases actually relaxes outwards because of competing forces. But in almost all real systems, it tends to relax inward. Why do you think that is? Yes, Yo-Yo?
The surface strain is not put by the layer that by atoms that should be the surface strain.
True, but I'm not sure that that necessarily makes it relax inward. the reason it relaxes inward is because the bonds between the first and the second layer strengthen. That's really what it's a sign of. And why do they strengthen? Because the surface is under-coordinated. Remember, if you go to lower coordination, you're effectively, although you're losing energy, that's why there's surface energy, but the energy per bond is actually becoming stronger. Okay? Remember that I showed you the potentials for copper? Remember that for the copper 2 molecule, so where you just had one bond, had the strongest potential. Okay? The equation of state gave you, where your 12-fold coordinate gave you much weaker potential. So you see that in surfaces as well. If you cut away the bonds here, the remaining ones strengthen and they pull the layer in. Okay. The other problem that's common in pair potentials, which I won't say much about, is what's called the Cauchy problem, that if you write down the relation between the stress and the strain tensor, and so this is the matrix of elastic constants, that for pair potentials C12 and C44 are always the same. And this has something to do with there actually being a zero energy strain mode. Remember that I showed you this? It's related to the same issue, that in a cubic or in a square model, you can actually kind of slide it without any energy change. And that actually puts a constraint on the elastic constant, which essentially translates to C12 being C44. And the last one, you know, if you're a practicing material scientist, maybe one of the important ones, that you can essentially not predict crystal structure in anything that's covalent. And you know, metals are covalent. I know they teach you there's metallic covalent and ionic bonding, but metallic is just delocalized covalent. And the reason is, I think you can already see, first of all, potentials tend to go to close packing, always. Because, you know, they want to have as many atoms around them as possible, because that's how you bring the cohesive energy down. And they don't count that cost, that if you bring more around you, your bond strength weakens. Okay? And they have no directional dependence. So they miss those two important components to get crystal structure right. You can actually do some theory about this, which was done already in the 70s, that you actually need what's called at least the fourth moment of the density of states to get crystal structure right, and that turns out to be at least a four-body effect. So if you actually thought of potentials as an expansion, say, you know, I'm going to write the energy as a constant plus an expansion in two-body terms, three-body terms, four-body terms, etc., which we don't even know if it would converge, you would have to go at least up to the fourth order to get crystal structure differences right. Okay, so how do you fix the problem? There are essentially, you know, if you look at the literature of empirical models, two avenues to go. You can either make what's called cluster potentials, and you know, so if you don't like a two-body potential, you can make a three-body potential. And the advantage of that, once you have a three-body potential, you can see angular dependence. Because, you know, if I have three atoms and they don't interact just pairwise, but there's a true three-body, I can say include this bonding angle. You know, a bonding angle is truly a three-body concept. Okay? So you can start building in angular dependence. The other direction to go is go to pair functionals. So you still want to write the energy as pairwise, some pairwise summation. You just don't want the cohesive energy per atom to go linear with what you sum pairwise or what you sum as its environment pairwise. So we're going to deal with both in class. Today I'm going to mainly do pair functionals. Pair functionals tends to be most applicable to metals, where I would say the square root dependence, that effect is strongest. Whereas cluster potentials or many body potentials in general tend to be more favored in the organic literature, both sort of organic chemistry, polymer chemistry, and so we'll go into that. Okay. So there's a whole class of methods which are called effective medium theories. The version of it that I'm going to discuss is what's called the embedded atom method, which is probably the most popular one. This was developed by Mike Vasquez, Murray Daw, in, I think, going back to the 80s, mid-80s or something like that. And it's probably now the most popular of the sort of empirical energy schemes. If you look back at those papers have now over 1,000 citations. And the idea is extremely simple. It's if you understand the source of the problem that our energy should not be linear with coordination, that's what you're going to fix. So in these models, what you do is you write the energy per atom as a function of the number of bonds around it. It's just that F should not be linear. Okay? And so that's why they call it energy functionals rather than a pair potential. The question is, how do you measure number of bonds? And if you sort of think about it, if you think yourself back in the 80s, how do you want to measure number of bonds? You don't really want to do it discretely. Okay? Because you could say, well, maybe I'm just going to count atoms within a 2-angstrom radius or some radius. The problem is, as soon as you measure it discretely, you're going to have to deal with discontinuities. As atoms move in and out of that radius, suddenly, you got 14 things around you instead of 15. So you would always have super large forces because of those discontinuities around your cutoff interface. So what you need is a smooth count of coordination. Okay? And the one they came up with in the embedded atom method is literally you measure the electron density being projected on you from your neighbors. Okay? It's ironic that I'll show you later the formal justification for the embedded atom method, which has a lot more to do with quantum mechanics. But that was actually a justification after the facts. The original idea came up with sort of, you really want to have a continuous measure of bonding around you. And so the idea is that you're going to do something like, I have a central atom. I have other atoms around me. How do I measure how much these contribute to my neighborhood? Well, these have some electron density functions around them. Their atomic electron density. I'm sort of drawing. And they all project onto that central atom. You count up how much electron density project there, and that's somehow a measurement of your neighborhood. And you see that's going to roughly have the right behavior. It's continuous. As atoms move farther away, they still contribute, but they contribute less. So it is a continuous measure, and the more electron density you project, okay, either the closer by the atoms are, or the more of them there are. Okay. So this is the idea of the electron density. You're going to actually calculate the electron density on a site as a measurement, in some sense, of the coordination, as a sum of electron densities coming from its neighboring atoms, J. Okay. What electron densities you use is kind of less relevant. In the original embedded atom and in most embedded atom codes, still they use essentially the atomic densities. So people have calculated the atomic electron densities with hartree-fock methods, and they're actually tabulated in these Clementi and Rode tables. And I'm just sort of showing you this, that they're basically parameterized by a bunch of Gaussians, but you can get those. So you can get those functions. Let me skip through that. Okay. So remember that if you have, yes, sir. Correct. Correct. So you, well, it's a distance-dependent function. Exactly. Yeah. So it's sort of what people in quantum mechanics think of as sort of non-self-consistent methods. Yeah. You literally treat the electron density of the crystal as the overlap of the atomic densities of the atoms. Okay. The reason that saves you here is you're actually not going to do quantum mechanics on that density. Again, you're just using that density as some measure of coordination. So I skipped some slides. Oh, somehow I lost the slide in here. Sorry about that. Okay, you know what? I put it in the wrong place. Here we go. So the way you write the energy in the embedded atom method is you write it as the embedding energy, which is you sum over every atom and you're looking for its cohesive energy, which is some function f of the neighborhood measurements, which is the electron density at the site of I. And that's your summing from these functions f, which are the projected densities from all the other atoms j. Okay? So typically, so this is the nonlinear part of the energy. Okay? Typically that is supplemented with a pair potential. Okay? So the standard embedded atom method is a pair potential, which is often just used for having a repulsive part, and a nonlinear embedding energy. So that means we have to solve three problems, really. The one we've solved. You need to know what the electron densities are. Take the Clementi and Röhre tables. You need to know what the embedding function is, and you need to know what the pair potential is. Okay. The pair potential used, to be honest, you can use almost anything. It's mainly used for the hardcore repulsion part. You don't want the atoms to fly into each other. Typically, they use some screened electrostatic form, which is essentially the product of charges, charge distribution functions on atoms. But you know, nothing would stop you if you really wanted to from using a Lennard-Jones. I'll show you in a second that there is ambiguity about the division of energy between the embedding part and the pair potential is not unique. Okay, so that means every time you change your pair potential, you'll have to change your embedding function. I'll show you that in a second. What do you use for the embedding function? You know, there are two ways that it can be done. People have written down analytical forms with some theoretical justification that I'm not going to go into. There's actually an excellent review article on the embedded atom methods, which we post just for internal use on the website. It's a 1993 Material Science and Engineering report. It's a really long paper, but it's really an excellent paper. So there are analytical forms, and here's a few of them given, and people have come up with other ones. More and more now what people simply do is tabulate the embedding function. And really what they do is they tabulate it so that you exactly reproduce the equation of state. What is the equation of state? The equation of state is energy versus volume or lattice parameter. Okay? So say at every lattice parameter you could try to get that energy with a better method, say quantum mechanics. Okay? And then fit your embedding function so that you exactly reproduce that. Okay? And so often the embedding function is tabulated. But commonly it has this form, you know. It's decaying, it's sort of decreasing convex, decreasing in energy and convex. And it needs both those properties. Well, why does it need to be decreasing in energy? Because, so this is the embedding density, and this is the value of the embedding function. Of course, as you put more density on a site, that comes from more neighbors, so your cohesive energy should be going down. Okay? That's why the energy of the embedding function goes down, but it needs to be convex, because convexity gives you sort of the correct behavior. Convexity really tells you that, you know, adding a bond going from here to here, let's say a bond is adding 0.01. So if we added a bond here, we'd get this change in energy, embedding energy. If we added it here, we'd only get that change. Okay, so the function has to be convex. In some sense, the decrease has to be per unit, and electron density has to be less for higher densities than for lower, and that's the definition of convex. Okay, the slope of it has to be increasing of this function. And you see that's going to, by construction now, get some of our problems right, because this shape of the function, the convexity, is what tells you that, you know, the low coordination bonds are stronger than the high coordination bonds. Okay. So you can already guess from this that we're going to get a lot of things right. Okay. And I'll show you some examples in a second. One what's the physical concept that sort of justifies the embedded atom method? There are things you can do formally in ab initio theory showing that, like in fairly simple tight binding models. So these are things that have the structure of a proper quantum mechanical Hamiltonian, but but they are parameterized forms of a Hamiltonian. But still, what they all tend to show is that the cohesive energy in highly delocalized systems to first order goes like the square root of the coordination. Okay. So you can give some justification for this nonlinear behavior. A somewhat intuitive concept of where the bonding energy comes from is that actually, if you put an atom in a metallic solid, where does it get its cohesive energy from? For the most part, it gets its cohesive energy from the delocalization of its electrons. Okay? And that's largely a kinetic energy effect. Remember that the kinetic energy in quantum mechanics is the curvature of the wave function. It's, what is it? D squared phi, dx squared, if you do it in one dimension. Okay? So highly curved wave functions have high kinetic energy. Okay? So if you can actually delocalize, your wave function becomes, in some sense, much smoother, with much less curvature, and you have lower kinetic energy. So if you believe that a lot of bonding cohesive energy in delocalized solids comes from that, then the measure of cohesive energy is essentially how well you can delocalize. So what do you measure with the embedding density? If you measure the electron density coming from atoms, the reason this works is that that's probably a very good measure over the number of states you can delocalize over. Things with higher electron density tend to have higher number of states, higher densities of states. And so you can delocalize over more states. And that's the somewhat intuitive explanation for why the embedded atom works. I mean, people have given somewhat other explanations. They could say, well, the electron density that I see from a neighboring atom measures the number of electrons I can bond with. But that's not totally true, because if those electrons come from a filled shell, there's nothing I can do with them. Okay? So somehow I tend to believe more it's really a measure of the delocalization you see. Okay. The embedded atom method is, yes, sir. Correct. Yeah. Yeah, so in an atom, you actually have a much higher kinetic energy because your state is much more localized. The embedded atom method is probably the most popular one of all these effective medium theories, but you'll see other ones with other names that are in spirit very much the same. Things like the glue model, Finis-Sinclair potentials, which slightly predate the embedded atom method, which are also nonlinear potentials. So they're really particle potential functionals, pair functionals, and the equivalent crystal model of Smith and Banerjee. These are all exactly in the same spirit. The brilliance of the embedded atom method was essentially that it was something for nothing. The computational cost is essentially the same as for doing pair potentials because you sum things only pairwise. If you think of what you need to do an embedded atom calculation, so you have your pair potential, that's a pairwise sum, but your embedding energy is also a pairwise sum. Because what you have to do per atom, you just have to sum the electron density coming from a bunch of other atoms around you. So that's a pairwise sum. And then you just have to stick it in F, okay, which is an extra evaluation. But embedded atom fundamentally scales only like n squared. So that was the brilliant part of it, or in the end, that's what made it successful. You could essentially do much better things with almost the same effort as pair potentials. And that's why it sort of took off as a method, and pretty much anybody in metals now would use embedded atom if they want to get any physics right. If you sort of want to do demonstration projects or things, like you want to do billions of atoms, there can be reasons to go to much simpler forces still to evaluate. But in metals, there's really no reason not to use EM over simple pair potentials. Okay. You know, what do people fit to? People fit to anything, like I told you before. The original EM potentials were fit to a standard set of data, which was lattice parameters, sublimation energy, you know, elastic constants, and vacancy formation energies. Now you'll regularly see papers in the literature, you know, claiming I have a better potential than you for aluminum, and I have a better potential than you for nickel, and some of that is true. So people are now in the game of kind of super optimizing these potentials for what it's worth. But the original database was a set of standard potentials, largely on noble metal alloys. People have spent a lot of time finding better potentials on technologically important alloys like nickel aluminum. You'll find probably at least 5 potentials who all claim to be better than somebody else's potential on the nickel aluminum system. So what I want to do now is just show you some results. And we're not going to analyze it in great deal, but I want to show that to you so you get some idea of what people do with this stuff. Here's linear thermal expansion for a bunch of sort of late transition metals calculated in EAM and calculated in experiment. And you know, these agree pretty well. That's maybe not a big surprise in close-packed solids. The thermal expansion is largely a measure of the asymmetry of your equation of state. Okay. I mean, in complex materials, that's not true, but in simple close-packed metals, if you get you remember your equation of state is slightly asymmetric, you know, it curves less towards the high lattice parameter than the low lattice parameter. So if you draw, you know, energy versus volume, you know, it's asymmetric around the minimum, and that's why you have thermal expansion. If you think about it, it's slightly easier to fluctuate to the higher volume than to the lower volume. Okay. Yes, sir. Oh, good point. There is, of course, no temperature dependence in the potential itself. So to do something like thermal expansion, okay, you either have to do a dynamic simulation like molecular dynamics, and we'll come to that. So, or you have to explicitly calculate the entropic factors that give you thermal expansion, which is essentially the dependence of the phonon frequencies on volume. So you can indirectly calculate the thermal expansion, but we sort of haven't gone into, we will go into molecular dynamics, but of course in the potential there is no temperature dependence. Okay. Here's activation barriers for self-diffusion in metals. These are almost too good to believe it. You actually don't get them this good with quantum mechanics. So it's almost surprising to me that they're this good if you compare EM to experiment. So this is the activation barrier for, I thought it was interstitial self-diffusion, but I'm not sure whether it was interstitial or vacancy self-diffusion. You know, here's a bunch of surface energies. These are not quite as good as the experiment. If you, for example, look at copper, here's the experimental number in ergs per centimeter squared, and here's the calculation on different facets. Because of course, often experimentally you measure some average of different facets. Unless you do careful single crystal work, you have some average. On the calculations, you have to calculate the energy on a specific surface, and that's actually one of the things you're going to do in the lab. So these are a little lower, you know, and that seems to be a rather consistent problem that, for example, also in platinum, you know, these are quite a bit lower than the experiments. So that may tell you that either there are more complicated quantum mechanical effects going on that you don't capture with these simple energy models. But sometimes it also means the experiment is wrong. I think in this case, the experiment, you know, platinum is a fairly easy metal to deal with clean. But surface energies of materials is sort of notoriously difficult to get experimentally. Here's a phonon dispersion curve for copper. Again, don't worry about the details. I don't want to show you the kind of things people do. Calculations are the lines, and the points are the measurements. Okay, so reasonably good at some of these high frequencies. There seems to be some problems with melting points. Again, this would have been done with molecular dynamics and then free energy integration. And again, for most materials, these come out remarkably well. If you sort of look at this, except again for the very late transition metals like palladium and platinum, there does seems to be some amount of problems. I'll tell you in a second about the limitations of these methods, and they may be related to the unusual electronic structure of palladium and platinum. Here's a pair correlation function in a liquid. People will get a grain boundary. This is something you simply could not do with a pair potential in metals, because when you calculate a grain boundary, you really are dealing with different coordinated environments. And the painful thing about a grain boundary is that you don't know ahead of time what kind of coordinations you're going to see, and you're going to see multiple coordinations. See, what people with potentials always did, if I know I'm going to deal with a surface, I can make a pair potential that's pretty good for those coordinations at the surface. If I deal with the bulk, I make a pair potential that's pretty good with bulk coordinations. But it's when you work with grain boundaries that you kind of end up with all kinds of coordinations, because the atoms in the grain boundary, some are high coordinated, some are low coordinated, depending on how the grains contact each other. Okay. So it's a great method, but it still has its limitations. One is that the bonding is spherical. Okay. You literally sum all the electron density coming from around you, and you literally just sum it up. You don't keep track of its orientation dependence. So, having one atom there next to me and one atom on that side is the same as having both straight in front of me. Okay? Because I just sum up the electron density coming from them. So it's purely spherical. That can be fixed. About in the 90s, Mike Baskus developed what's called a MEME, and that just stands for Modified Embedded Atom Method, which basically has embedding functions that keep track of the angular dependence of the electron density around you, essentially by mapping the problem onto spherical harmonics. MEME is not nearly as popular as the standard EM because it adds a level of complexity to the method, and it's not totally clear that you're making things work because the physics is better or you just have more fitting parameters. Mike Baskus originally developed a MEME to work on silicon, where angular dependence clearly seems to play an important role. Yes, sir? Mm-hmm. Okay. Well, your force is directional dependent because you're taking the derivative of energy with respect to a vector, which is, some distance. But again, the force will be directional dependent. Let me show you an example. Let's say I have a central atom here, and I got 4 atoms around it. Okay? The force will be directional dependent because if what is the force? The force is how the energy of an atom changes as I move it into a particular direction. So the force along this direction is the energy change as I move the atom along this direction, because it is the derivative of the total energy with respect to some unit vector in that direction. See, if I change it in this direction, I'm going to significantly increase the overlap with that atom. But if I change it, say, in this direction, okay, that's not necessarily the same derivative than in this direction. Okay? So the force will be directional dependent. okay, just because of the crystallography. But the energy is not. So what I mean with that is that, let's say, let's call this some unit length L, and they're all at L. Okay? If I do this, and here's my central atom, and these are all L. Okay? That gives me exactly the same embedding energy as in the first problem. Of course, the total energy will be different because these guys interact very closely. But the bonding energy of the central atom is exactly the same. And that's what I mean with no angular dependence. Okay? It doesn't, in the end, see what orbitals that electron density comes from. Okay? And when you think about angular dependence, in the end, what is it? It is polarization of orbitals. If I, think of sp3 bonding, what is that really telling you? If I do an sp3 hybrid along this direction, I'm really starting to polarize the orbitals along, 109 degrees in other directions. So I really need to try to get my bonds around in those directions. So that's essentially what angular dependence comes from. Does that help? Okay, you think so? Well, let me know if it doesn't. Okay. The other problem is, which is more a technical problem, is that the potential is not unique. And this is something you just have to be careful with if you start messing around with potential files yourself. If you're going to use it as a black box, you'll probably okay. But let me get you some notes on that. The way you can see that the potential is not unique, if I have an embedding function, f of rho, if I define another embedding function, let me call it g of rho, where rho is the electron density, and I say that's f of rho plus some linear term in rho. Okay. You can make the total energy function exactly the same with either of the two embedding functions just by changing the pair potential. And let me show you that. If I write the energy as the sum over atoms, the embedding function on that atom plus some pair potential part. Okay, let me substitute this in. Okay. So I get that this is sum I fi rho plus 1/2 some ij psi ij rij plus sum I k sum j not equal I of frj, where rho I was sum j f. Okay. Essentially what, if you want to look through the math, don't worry too much about it. If you do a linear transformation on the embedding function, okay, you see this term is linear in things coming from the atoms around it. Okay. It's linear in these electron density functions. So anything that's linear in functions that I sum from the other atoms is just like a pair potential. Okay, because that's what a pair potential is. I sum contributions, okay? I add up contributions from the things around me. So I'm linear in that contribution. So any linear part of the embedding function just looks like a potential. This is a pair potential. This is the sum over two indices I and j, and I add something up. So this I could just add to psi. Okay. So if I add psi to this and use the embedding function f, I have exactly the same as using the embedding function g and using just the potential psi. So the linear part you can move arbitrarily between the embedding function and the pair potential. Okay. So that tells you something else that's kind of important. When is a pair potential alone good in metals? It's when the embedding part doesn't change. If my atoms stay roughly at the same density, okay, then all the changes come from the pair potential part. Okay? So what would you do? Get another slide. You know, if you have an embedding function as a function of rho, if you're working, say, at this density, okay, let's sort of say the density of the bulk and you're studying bulk problems, okay, you could take the slope of this, take the linear term, make a linear approximation to that, okay, and add that to the pair potential, and now you wouldn't have to worry about the embedding function. Okay? So at constant density, pair potentials are actually pretty good. It's when the density around you, the electron density around you changes, which is in essence a measure of the coordination change, that you run into trouble. Okay? And so people have gone into that game of making density-dependent potentials. Okay? And so you would have a different potential when you're near a surface than when you're near the bulk. Okay. So my summary on effective medium theories, which I showed by embedded atom methods, is in essence that there's no reason not to use them. If you've decided you're going to use an empirical model for metals, there's really no reason at all to use pair potentials. You know, embedded atom basically does better at very little cost. Saying that it does better doesn't say that it does everything. And you know, I remember talking to people like Mike Vasquez who invented this. They're embarrassed for what the kind of things people now do with the embedded atom method. Like with any successful method, people push it way too hard and try to calculate all kind of subtle energy effects that it just never was made for. And you see people write papers on, you know, if I change my constant by, you know, 1,000 here, I can get this phase correct and so. But in the end, you know, it gives you these gross coordination effects right. But it does not give you very subtle hybridization effects, right? You know, why, for example, were platinum and palladium not so good? Because, you know, platinum and palladium have almost filled or filled d bands, okay? And as a function of the environment around platinum and palladium, there is very subtle electron transfer between the d band and the s band, okay? And when you're just measuring electron density, that all looks the same, but those states behave very differently. Okay? So there will be always subtle electronic changes that you simply won't get. And if your system is really influenced strongly by those, okay, you won't get them right. For example, people try to get complex crystal structure differences in metals with EM. You will just never get there, period. If you look at, you know, let's say you make an alloy, palladium, ruthenium, whatever, you know, the crystal structure energy difference in that material, like in most metals, over the order of 5 to 10 millielectron volt. You know, you cannot get things right on that scale with these kind of simple models, so you shouldn't try too hard. But on the other hand, you know, if you're going to study, say, I don't know, fracture in a material, in a simple element, like one of these big movies I showed you, that's to a large extent a topological event. Okay, you know, you will get a lot of essential pieces of that right, because you know what is that? That's a coordination change event largely. You will get a lot of that right by doing EM over potentials. Okay, this is a great website. I only added that this year to the lecture. I found this. There's a group in Japan that calls themselves the EAMers. They even have a blog now. And so, you know, there's a lot of cool stuff you can download. They have potential files. You can get the EM code from the Sandia side. It's a little hard to get to because Sandia being a national lab, you know, they're totally paranoid about anything, downloading anything. But there are sources where you can get the EM code. It is technically freely available. It's just not necessarily trivial to get to it. Okay. So we talked about pair functionals, which was this direction. So the other direction is obviously to go to cluster potentials. So, well, you know, I don't like my expansion in just 2-body terms. I'll start adding 3-body terms. Okay? It's the obvious extension, and if you don't like that, you can go to 4-body terms. That's definitely done, and for reasons I'll go into the sort of next lecture on Tuesday. It's extremely popular in the world of organics, where it's actually really, really powerful, and we'll go into why that is the case. But a typical material in condensed matter, where obviously this was done, was silicon. Silicon is a low-coordinated solid. It's only 4-fold coordinated in a diamond cubic structure. It's extremely hard to get that with a pair potential, you know, because again, your system will always try to form FCC or HCP, essentially. So what you can do is build a 3-body potential that favors these 190-degree tetrahedral angles. And as soon as you do that, if you actually make that force strong enough, you can do almost nothing else than form diamond cubic. Because diamond cubic is basically the way to pack atoms and put them under all these 109 point, what is it, 0.4 or something, degree angles. Okay. So if you make a strong enough 3-body force, you will, by definition, end up in the diamond cubic structure. If you work with 3 coordinates, you can also transform that and instead work with 2 distances and an angle. So, you know, if I have 3 atoms, the coordinates of them, I can also always say that to have the relation between them, I just need to have these 2 distances and this angle that fully defines the 3-body problem. And that's usually how it's done. People have pair potentials that take care of the distance dependence of that. And then they have an angular potential, which takes care of the angle between these. And often the prefactor of the angular potential will have some distance dependence in it. Because, of course, maybe you want to enforce this 190-degree angle when your 2 other atoms are close, but when they're very far, you don't really care anymore. What's the possible choices for angular potentials? The simplest one is simply a quadratic, a harmonic function in the angle. Okay? If you want to impose an angle theta naught, you make a potential, you know, that's literally a quadratic around theta naught. Okay? So extremely simple to evaluate. So that function is actually often used. You can also use, the disadvantage of this one is that it's not periodic. And sort of angle measurements should be periodic. So you can kind of get into trouble with this if you go too far from equilibrium. So another thing you can use is a cosine function, which has the proper periodicity. You know, if you take, I don't know, 109 degrees or whatever angle you want, or you take its complement, 360 minus that, you should get the same answer. And so cosine functions will do that right. And this one, cosine theta plus 1/3, this part is minimal when theta is 109, the tetrahedral angle. Okay. Excuse me, losing my voice. So it works working with 3-body potentials. It's of course more work. It's now ordered n cubed. Because for every atom, you now have to look at distances and angles with pairs of atoms. Okay, so it becomes an n cubed operation. So it's more work. And calculating the forces as the derivatives of the energy is also quite a bit more work. Okay, you know, the most famous 3-body potential is probably the Stillinger-Weber potential, which, as you can see, has this cosine theta form for the, this is the angular part. This is the distance dependence of the angular part, so how much should you penalize angular deviations as the distance gets further, and then this is the 2-body part, which is sort of a Morse-like potential. Originally, Stillinger-Weber, when they actually wrote down the function, they didn't even fit it very carefully. I mean, it was a great form, but they just kind of like, did a rough fit. And so the original Stillinger-Weber parameters and the ones people now use sometimes more recently are not the same anymore. The potential has the same form. But some people have done recently better fits. So when somebody says the Stillinger-Weber potential, there are variations of it for the constants. So what do you get right with something like a Stillinger-Weber potential? Well, you can kind of guess, why people did this, because silicon's so important. They wanted to be able to model silicon right. So it's important to understand which pieces you get right. One of the critical issues was surface reconstruction. If you take silicon 100, if you truncate it, it actually undergoes a 2 times 1 reconstruction. What essentially happens if you take these top layer atoms, okay, these only have, they're only bonded to 2 atoms below them, and so they dimerize on the surface. So basically, these move together in sort of double rows. Give me a better color. And then these will move together. And so they double the periodicity in one direction. And so you have these dimers that form. And because of that, the surface atom is bonded to 3 other atoms, 2 below it, 1 other in the surface, and so they're better bonded. And that's the 2-by-1 reconstruction. The 2-by-1 reconstruction you get right with the Stillinger-Weber potential. You'd actually get it right with almost anything, because it's essentially a topological reconstruction. Atoms like to have more atoms around them to bond, period. And so that's what drives the 2-by-1 reconstruction. That the top layer atoms now are at least 3-fold coordinated. And they're actually almost 4-fold coordinated instead of 2-fold coordinated at a just unreconstructed terminated surface. But here's the reconstruction on the 111 surface. The reconstruction on the 111 surface is 7 by 7. So it forms a much larger unit cell on the surface. And that is not reproduced by the Stillinger-Weber potential. So clearly that's a more subtle effect. Okay. Silicon, being such an important material, has a multitude of potentials. Everybody has made one and claims theirs is better than yours. And I just show this graph not for the details, but to show you that this isn't even a tenth of the potentials made for silicon, but it's some of the famous ones. SW Stillinger-Weber, Bismuth-Harman, and the Tursoff potentials, which are quite famous for silicon, are not even on here. But if you see, this is the angular part of these potentials. Is very different. Okay, they all give the same answer on static properties, like the elastic properties of silicon, the cohesive energy, the lattice parameter. But it's sort of divided differently between pair parts and angular parts. This one clearly wouldn't give you the same stiffness of bond bending, okay, around the typical dihedral angle. And that shows up. There's what I thought was a really nice paper. And I'm sorry. Oh no, the reference is here. This is the Nurminen paper from Physical Review B. They did what I thought was brilliant. They did exactly the same simulation with 3 different potentials. This is the left is the Stillinger-Weber potential, and then middle column is Tursoff 2, which is the Tursoff potential, and then Tursoff 3. So they did exactly the same Monte Carlo simulations with the 3 potentials. And this is the 001 or 100 surface of silicon. So remember, that's the one I showed you before that dimerizes. Okay, and so the top line is at low temperature. Tursoff 3 doesn't dimerize. Tursoff 2 does sort of dimerize, and so does Stillinger-Weber. But they look slightly different, but these are in reasonable agreement. If you go higher in temperature, okay, then Tursoff 3 dimerizes, so does Stillinger-Weber, but Tursoff 2 starts kind of looking quite different already. So these are potentials that if you looked at how they reproduce static properties, they all do extremely well. Okay? But it's extremely hard to fit to dynamical properties because you don't have that as quantitative information very often. Like, you know, first of all, we don't know what the right answer is here. Okay? But even if we did, let's say somebody does brilliant STM, you know, and we know what the right answer is, it's very hard to feed that back into a potential. Okay? And so, you know, the reason I'm telling you this is not to dissuade you from using potentials when you need them. It's just to make sure you're cautious. Okay? You know, there's a big reason that people do ab initio calculations these days, and it's not because they necessarily like it, but it's because the results tend to be more reliable or at least predictable. The errors are more predictable, let's put it that way, which is a useful thing to have. Having error is one thing, having unpredictable error is a lot worse. Okay? But there will always be problems where they're just too complex, or you want to do them fast, where you want to use pair potentials. Just don't always believe everything you see. Okay? And try to fit as close to where you're going to explore the physics. That's essentially meaning. Okay, here's a bunch of references. I'll actually put these on the Stellar website. We'll finish the empirical potential lecture. We'll go into organics and a little bit of polymers on Tuesday. And then Professor Marzari will start giving an introduction to basic quantum mechanics, and then we'll start sort of ab initio energy methods. And Professor Marzari will do that, but so I'll be still lecturing on Tuesday. So have a good weekend, and I'll see you on Tuesday.